In this video, we're going to discuss the concepts of acids and bases. This is a topic we've talked about earlier in the year, but this time around we're going to add a little more detail to that discussion. Let's begin by talking about the learning objectives of this video. We're going to start with a quick list of some properties that go along with acids and bases. We're then going to move the discussion into some models used to describe the characteristics of an acid and the characteristics of a base. The first model that was created was something known as the Arrhenius model. We'll begin by defining that model, but end up really spending most of our time talking about its limitations. It's not really a model that is employed today in order to describe acids, except for a couple exceptions. A better model, or at least one of the better models to describe acid behavior, is the Bronsted-Lowry model, came up by two separate scientists. We'll begin with the definition of what this model is. We'll then move into talking about the acid-base conjugate concept, as well as the hydronium ion. When all is said and done, we'll finish up the discussion with an idea of what acid strength is about, but again, this is the discussion we'll save for more detail for later in the year. Let's begin by talking about the properties of acids and bases. We'll start with acids. We'll talk about taste first. We don't usually go around tasting chemicals, but acids do show up in a lot of foods, and when they do, they often taste very sour. Down at the bottom of the page, you can see the picture of the lemon there. One of the primary ingredients of lemons is citric acid, which gives it that characteristic sour flavor. As we'll talk in a subsequent video, but you should have seen in prior classes, we can measure the pH of an acid, and acids generally have pHs less than 7. That's one of the things that defines them as an acid. Acids are also characterized as being electrolytes in solution. This will come up into play when we talk about the idea of strong versus weak acids. Acids react with carbonates to produce carbon dioxide gas. If you ever added acid to baking soda, which is sodium bicarbonate, you've seen this very violent and interesting reaction before. And finally, acids react with metals to form hydrogen gas. And this is actually, again, something we've done a couple times this year, where we've added a little bit of metal into a solution of hydrochloric acid, and we've seen those hydrogen gas bubbles form. Moving on to bases, bases tend to have a bitter taste to them. We don't see bases in food that much, but if you've ever gotten a little bit of soap in your mouth, as pictured below, you can recognize that bitter taste. Bases, by definition, have a pH that is greater than 7, and they are also electrolytes in solutions. One of the big characteristics you can know when you're handling a base is it'll feel slippery in your fingers. Again, when you have that soap in your hands, you can feel that slipperiness. Now that we have the basic properties of acids and bases under control, we can start talking about some of the models used to describe the chemical behavior of an acid. One of the first models created was made by a scientist by the name of Svante Arrhenius. He was a Swedish chemist and physicist, and is often credited with the founder of physical chemistry. This is a branch of science that deals a lot with the mathematics and calculations behind a lot of the chemistry that we do. Now, in a lot of cases, we spend time talking about the Nobel Prizes that scientists have received. Arrhenius is actually famous for not only having a Nobel Prize of his own, but he's one of the scientists credited with setting up the Nobel Prize Foundation and the Nobel Prize Institute. So he's one of the people that put this whole process into order. He then, later on, received his Nobel Prize in 1903. In terms of science, Arrhenius is famous for coming up with a model to describe acid behavior, as well as a calculation known as the Arrhenius equation, used to talk about chemical kinetics. Interestingly enough, and seemingly unconnected to a lot of his other research, later in his life he actually did a lot of calculations on the greenhouse effect, and was one of the first scientists to actually model this behavior where gases, certain types of gases, can collect in our atmosphere and raise temperature. And some of the equations that he used, or he created in this process of his research, are actually still used today to model the greenhouse effect on our planet. Now let's move on then to the work that Arrhenius was able to do, and he came up with the Arrhenius model of acids and behavior, and he came up with a definition of what it means to be an acid and what it means to be a base. We'll start with that acid definition. According to Arrhenius, the definition of an acid is any chemical that produces H+ ions when in solution. As an example, we can deal with HCl. HCl, as hopefully you remember from our naming rules, is hydrochloric acid. The name implies it is definitely an acid. When we can see in this net ionic equation here, when HCl is dissolved in water, it separates into H+ ions and Cl- ions. Because it creates these H+ ions, according to Arrhenius, this is what makes hydrochloric acid an acid. Moving on, we can talk about his definition of a base. In terms of a base, in terms of Arrhenius model, it's any chemical that produces OH ions when in solution. And again, one of the most common bases we can consider is this guy, sodium hydroxide. When sodium hydroxide dissolves in water, we get these sodium ions. and we get these OH ions. And because sodium hydroxide produces OH ions, according to Arrhenius and his model, sodium hydroxide, the original chemical, must actually be a base. As I said already, this is the first major model that is used to describe acid-base behavior. It certainly has its merits, and at the very, very least, it set the stage for concepts like pH and the concept of acid strength, all things we'll talk about a little later on down the road. Now, unfortunately, Arrhenius' model, while a great start to understanding the behavior of acids and bases, has some pretty serious limitations. According to Arrhenius, the only chemicals that can possibly be an acid or possibly be a base are the ones that contain these two specific ions. But as scientists started working more and more with chemicals, they started to realize that there were other substances that had similar acid-base characteristics but didn't fit this very narrow definition. A great example of that would be the chemical ammonia, NH3 down here. When NH3 is placed into water, we can measure its pH, and it gets a pH of approximately 11. If you recall back from our discussion before, things with a pH of 11 are characterized as bases, but there's nothing about this NH3 that would be able to produce OH ions while in solution. Therefore, again, we can see the limitations in Arrhenius models, and scientists seeing these limitations were able to go further and develop a model that built off of this to come up with a better explanation of what an acid and what a base must really be. This brings us to a pair of new scientists that had actually nothing to do with one another, and neither of which were very interested in the research of acids. The first one we'll talk about is a scientist by the name of Johannes Brønsted. He was a Danish physical chemist, and he was doing research on the concept of electron affinity, which is a characteristic of an atom's attractive force on electrons, something we'll tackle a little bit later in the year. In the course of his work there, he found that Arrhenius' model of the atom was not sufficient to explain the things and the characteristics he was seeing, so he developed something known later on as the protonic theory of acids and bases. And that's what he's most credited for working with. Just to give a little more history upon the idea of Bronsted here, during World War II, this is around the time he was an active scientist, he actually spent a good chunk of his time opposing the Nazi regime, and was later actually elected to Danish Parliament as a result of his activity during the war. Unfortunately, though, he died before taking office. But again, yet another credit to a great scientist's life. The second scientist in this discussion was a scientist by the name of Johannes Lowry. He was an English physicist, or an English physical chemist. Again, we're talking countries apart, these two guys. His research was focusing on a concept of optical rotation. He was doing research on chemicals that have different characteristics, whether you have a particular isomer or with the other isomer. And as a result, again, he was dealing a lot with acids and bases and found that Arrhenius' model was not sufficient to describe the things he was trying to do. He simultaneously came up with the protonic theory of acids bases along with his counterpart Bronsted, and both of them are eventually credited with the discovery of this particular idea. As in terms of his success along with this, he was eventually named a Fellow of the Royal Society, which is a very high honor that can be associated to people in the country of England. Again, together, both of these scientists came up with what is now known as the Bronsted-Lowry model of acids and bases. And we're going to now redefine what an acid and a base is in terms of these two guys' protonic theory of acids. In the Bronsted-Lowry model, then, an acid is something that is considered a proton donor in solution. And you'll notice we have a similar reaction we had before, but this time it's going to be HCl plus water. And what we see happens in HCl plus water is that the hydrogen atom here is donated to the water molecule. We create a very peculiar substance known as H3O. And we'll talk about what this is in a moment. That leaves this concept, or this extra ion of Cl minus behind. We still get our charge balance here, but again, it's an acid because it has donated a proton to the solution. Where the models start to differ significantly is when we start talking about Bronsted and Lowry's description of what a base was. And according to Bronsted and Lowry, a base is something known as a proton acceptor. It accepts protons when in solution. For example, we can talk about this particular chemical here. This is NH3 ammonia. Now, according to Arrhenius, this would not be a base. It has no OHs in it. However, it can take an H plus from water, which in this scenario is now behaving as the acid because it's donating a proton, and the NH3 can accept that proton to become NH4 with a +1 charge. And notice here's what we create when we get into solution. Here's that OH that we've been looking for. Even though ammonia, NH4, didn't have the OH in it, notice by using water we're able to create that OH right here, hence the behavior of being a base. This model, as I already said, is very similar to the Arrhenius model, but it's a little more flexible. It allows for a wider definition of what acids and bases are to encompass chemicals that have acid-base characteristics but didn't fit the narrow description created by Arrhenius. Now, to take things a little further and maybe explain some of the stuff from the previous slide, we have to talk a little bit more about the behavior of water, because water is a very interesting chemical when it comes to dealing with acids and bases. We would describe water as something as being amphoteric, meaning water can act as both an acid and a base in the Bronsted and Lowry model. Again, we can take a look at a reaction down here, and I can react a water molecule with a second water molecule. Well, one of these water molecules can take its proton and donate it to the other. That makes this guy an acid in terms of the Bronsted-Lowry model, and that makes this water molecule a base in terms of the Bronsted-Lowry model. And again, we create the H3O plus ion and we create the OH minus. This process is not known as the auto-ionization of water, because water is automatically, with just itself, separating into separate ions. Now, of course, these ions are relatively unstable and they will naturally go back to the H2O and the H2O again, but this is a process that can go back and forth. Really what you want to take away from this is that water can act both as an acid and a base, and that's going to be important in our later discussions. Something else we want to point out, there's a new type of ion that we've talked about a little bit, but maybe now it's time to take a minute and put a name to it. A better description of an H plus ion in solution, it doesn't really exist as an H by itself, but rather as an H attached to a water molecule, and we get this H3O plus. This is known as the hydronium ion, and again, when you're working with the Bronsted and Lowry model, the hydronium ion actually makes more sense to discuss than just the H plus that we had from the Arrhenius equation. Really what we get here is the fact that water is acting as a source and as a repository for protons in the Bronsted-Lowry model of acids. I have atom down here. That's a little incorrect. So we have acids. It can be a base, meaning it's accepting the protons, or it can be an acid, meaning it's donating the protons, and it depends on what other chemical compounds we combine it with. Just to wrap up this discussion of the Bronsted and Lowry model, then we have a couple new definitions we can talk about. We've already identified what an acid and what a base is, and now we're going to talk about their conjugate pairs. So for example, we can talk about what a conjugate acid. Well, a conjugate acid is the acid that is made when a base accepts a proton from a hydronium ion. When you have that base, say for example, the NH3 we had from before, and it turns into NH4 plus, well, here it's a base because it's accepting a proton pair, but after it's accepted that proton pair, now it's actually capable of donating that something else, or that proton pair back to something else. This means it's now an acid. So when you react a base and create an acid, you get those conjugate pairs there. Likewise, we can have the opposite. We can have a conjugate base. The conjugate base is the base that is made when an acid donates its proton. So like I said, we can start with that HCl, which is definitely an H plus donor, and that's going to create the ion Cl minus. Well, Cl minus is now something that's capable of receiving an H plus to create HCl again. Since it's an H plus acceptor, it's now a base. So we end up looking for these conjugate acid and conjugate base pairs, and there should be two pairs of them in each reaction. So just as a quick example, we can talk about the ammonia reaction before and identify what the acids and bases are in this reaction, as well as identify what the conjugate acid and the conjugate base is. As we've already talked about, NH3 plus, or NH3 by itself, is going to accept a proton from the water, which means that NH3 is going to be our base in this reaction, which means also that H2O is going to act as our acid in this reaction. It's the proton donor. At the end, after the NH3 has accepted it, now this guy has the extra proton here. You could imagine then that that extra proton could hypothetically then recombine with our OH to create the water again. This makes the NH4 plus the conjugate. This makes it our conjugate acid, and it's paired with the base that we originally started with. So this is the conjugate acid of the original base that we had. And that makes the OH minus our conjugate base. And again, this conjugate base is then paired with the original acid that it started with. As we'll talk later on, we'll talk about the idea of acid strength. What we'll mention is, in fact, we'll come back to this idea, is that a strong base is going to make a relatively weak conjugate acid, and a strong acid is going to make a relatively weak conjugate base. And we'll talk about the fact that that base concept, strength concept, has to do with the ion's affinity for those protons. So here we are with that acid strength concept. Now we've already talked about this idea of strength in terms of electrolytes. We talked about strong electrolytes versus weak electrolytes, and the exact same concept comes along here. A strong acid is an acid that completely disassociates in water. So for example, HCl is going to be one of our strong acids. When it goes into water, it creates H3O, and it creates the Cl minus, and this happens 100%. Every single HCl we start with makes its way over into the product. There's no leftover HCl when we're done. This happens, it has to do with the fact the affinity between the H plus and the Cl minus versus the affinity of the H plus over here to the H2O. Because this H plus is more attracted to the H2O, it's going to separate very quickly and very easily, and as a result, we get 100% separation. So this is what we're going to talk about when we're dealing with a strong acid. Weak acids are kind of the opposite. In a weak acid, we only get partial dissociation, just like when we had a weak electrolyte, we only got partial dissociation. As a result of that, we're not going to get as many H3O plus ions in solution as we would if we had a strong acid, because only some of this strong acid, and we'll use this example down here, H2C2O3, this is actually acetic acid. When acetic acid goes into solution, it separates into the two separate ions, but those two separate ions then are capable of reconnecting back together. Notice I have the arrows shown in both ways here, to go back and separate back again into water and the actual molecule HC2H3O2 again. As a result, like I said, we're going to have fewer of these guys in solution, which means our acid's going to have less strength to it. So some of them, as we said, stay as whole acids, meaning the pieces stay together, and some stay as separate ions. As we get later in the year, we'll talk more about this process. This is something known as an equilibrium, and we'll get into more detail there. That being said, since we're not talking about this equilibrium for now, most of our time and energy is going to be spent dealing primarily with strong acids, and we'll save this concept for a couple months from now. We can discuss equilibrium. Just like before, though, before we wrap this up, because in this situation the attraction of the hydrogen to the water was greater, all of this reacted and we got 100% H3O ions. In this situation, the attraction of the H plus to the acetate ion is stronger actually than it is to the water, and as a result we get fewer of these H3O ions produced. And again, we'll talk more about what fraction goes back and forth when we discuss that idea of equilibrium. Just to wrap things up in terms of our discussions of acids, we have a list here on the left and right of things that would be considered strong acids and other chemicals that would be considered strong bases. Notice all the strong acids start with that H plus, and notice all the strong bases have this OH minus in them. There are definitely lots of other bases besides this, but if you're dealing with a strong base, we're going to expect to see that OH. I think it's important to take a minute and jot these strong acids and strong bases down. The assumption you can make with this list is that any other acid or base is weak. And again, this is something we'll tackle later in the year after we've had a little discussion on equilibrium and then are better equipped to deal with the concept of what a weak base would do as opposed to a strong base or a strong acid would do. Aside from this is basically it in terms of what you guys need to know about acids. In future videos, we'll develop this further and do some of the calculations, some of the mathematics that goes along with this concept.